Hi, I'm Laurence.
And I'm Anna.
This is the second video in a series of 3 about the double-slit experiment. In this video, Anna and I explain why observing a light wave causes it to disappear.
In the first video, we learned what happens when electrons are fired at just the right-hand slit in the double-slit experiment.
The results showed bands of light on the back screen, which indicated that light was passing through both slits and creating an interference pattern.
To detect if electrons were entering the left-hand slit, even though they were not fired in this direction, scientists used an electron detector. When the electron detector was used at the left-hand slit, the pattern on the back screen changed, from multiple bands of light to just 2 strips of light. That corresponded to the slit's positions.
We must clarify at this point that the commonly adopted phrase stating that quantum events change when observed is stretching colloquial language to the absolute limit. Electrons are too small to be observed. Instead, they are detected. Yet, maybe having the electron detector directly in front of the left-hand slit compromised the result somehow. So, the following experiment was to move the electron detector away from the slit and position it halfway between the slit and the back screen.
The results were the same. Just 2 bands of light on the back screen, which corresponded to particles, and not an interference pattern caused by diffracted light waves.
The 2 bands of light on the back screen had never been seen before when firing light through narrow slits, as this creates diffracted light waves that interact with each other and form an interference pattern.
We know that the light that passed through the slits had become diffracted waves, yet the experiment showed that observing the diffraction pattern caused the waves to behave like particles, leading to the conclusion that the diffracted waves had transformed into particles when observed.
We also know that when diffracted waves reach the back screen, they are realized as pinpoints of light. When they encounter the back screen, they transform from a pair of diffracted waves into a single light particle.
The back screen causes the diffracted light waves to form particles of light, because light waves are massless radiation, composed of oscillating electromagnetic fields that undergo changes when they come into contact with objects.
The same is true when the diffracted light waves encounter the electron detector. They become particles, but only for the briefest moment.
To demonstrate the phenomenon, we will fire electrons through a single slit. The diagram illustrates an electron gun that fires electrons, which then propagate as waves, as they travel towards the slit.
When the light passes through the narrow slit, it diffracts, resulting in a wider wave pattern.
The diffracted light waves are oscillating electromagnetic fields that undergo changes when they encounter objects, and consequently, the electron detector causes a reaction that sees the waves transforming into particles.
But the transformation is short-lived, as light only travels in waveform, and the particle transforms back into a wave to continue its journey towards the back screen. But this light wave has not been diffracted.
The new light wave travels forwards, where it is once again transformed into a particle when it encounters the back screen.
From the electron gun to the back screen, whilst traveling at 300,000 kilometers per second, the following 5 transformations occur. Particle to wave. Wave to diffracted wave. Diffracted wave to particle. Particle to wave. Wave to particle.
Conducting the same experiment, but adding a second slit, demonstrates how the interference pattern is disrupted, and why 2 bands of light appear on the back screen.
The images and experiments we have described demonstrate why light changes from a wave to a particle when observed. However, the electron detector only detected part of a quantum entangled probability wave, whose twin was quantumly connected.
But that's the end of the second of 3 short videos explaining the double-slit experiment. We hope you enjoyed it.
Our third video explains quantum entangled probability waves.
We hope to see you there, or at www.quantummindcontrol.com.